Okay, I want your feedback after this. So I studied maths at university, and the kind of maths that I ended up falling in love with is a lot of the things that power asymmetric cryptography today and help us stay safe on the internet, sign our Git commits, all the things that you read in the abstract for this talk. My friend Daniel put his cat in his talk, so I've put my cat in the talk. This is Gothmog. She tries to stop me getting work done. So, the agenda for today, I am going to give you a brief history of cryptography and why it's useful, and I do mean brief. I'm going to talk about how RSA works as a very classical example of asymmetric encryption, and then we're going to talk about elliptic curve cryptography. There is a worked example of it at the end of this talk if we have time, but I suspect we won't. But the slides will be available for you if you do want to check that out. And I'm going to talk about quantum computing, and in particular Shor's algorithm and how it impacts the landscape of asymmetric encryption. So, and then what comes next after post-quantum cryptography. So, a brief history of cryptography. Let's say I want to send you a message and I don't want anybody else to know what it is that I've sent to you. I could do something very simple like this. I could say, I want to tell you that Devoxx is great. And in order to hide this message, all I do is I take each letter of this message and I shift it along in the alphabet. The English alphabet, I am English, unfortunately. I did think about trying to translate this talk into Greek, or at least these parts, but I didn't actually end up going through with it. But as you can see, I've got the first letter is D. You can see D goes to J, and in the output, that's what we've got. And this is called a Caesar cipher. Technically, this is military-grade encryption for the Roman military. And this is this is quite simple. It's simple to understand, and it's also simple to break, because you can do things like analyzing the frequency of letters in the output to determine what the mapping is. We can understand this kind of cipher in the following way. Each letter corresponds to a number, its position in the Latin alphabet, and all we're doing is we're adding 6 and then outputting the result, translating it back into letters and sending that. We can do more complicated things with this kind of system. In order to recover that message, the person who is trying to read it would need to know that this number here was 6 in order to shift everything back, right? We can do things that are a bit more complicated with this kind of system. So we've already got the idea that each letter is translated into a number. But we don't have to add just 6s to every number. We could add another word, right? Because every word can be thought of as a series of numbers. And then what we do is we add each number to its corresponding number from the secret that each person shares. And we get some numbers. We take the modulus of 26. There are only 26 letters in the alphabet, so that 33 becomes a 7. And we translate that back into a word. And now, if I send you this, you have to know that the word you have to subtract is secret in order to get back to the original secret encrypted message. Now, this is an example of symmetric cryptography, because each person in this exchange needs to have access to a shared secret. The knowledge that they have is symmetric, right? And this is very, very secure when it's done correctly. In fact, most web traffic is encrypted symmetrically using AES, for example. But it requires both parties to already have access to a shared secret. And this is difficult because how do you actually transmit a secret without somebody else listening in and compromising your encryption? So that's why we need asymmetric cryptography. Is a lot of the time, for example in TLS, the asymmetric encryption part of the process is actually just used to set up a big shared key for symmetric encryption, because it's much faster to do. And this is called key encapsulation or key exchange. I won't be covering specific mechanisms for that in this talk, but it's absolutely fascinating. So that is the setup to why we need asymmetric encryption and cryptography. And the most famous example that you learn about when you start learning about this is RSA. Now, the RSA crypto system was made public in 1977 by 3 mathematicians whose initials are RS and A, so that's the name. It was also independently developed by a mathematician in GCHQ called Clifford Cox, and it didn't become public knowledge until after RS and A had published their version. This guy, Clifford Cox, he sort of came up with this idea, and the people at GCHQ said, that's not interesting. That's not very useful. What are we going to do with this? And yeah, it turns out it was useful, and there is a lot you can do with it. So bit of an L for the British on that one. And the security of this cryptography system is based on the fact that if you have a big number, without loss of generality, an odd number, because you can't find its factors very easily. Obviously, it's an even number. You know that it's got a factor of 2, and you just divide by that. So if you've got a big number and you don't know what its factors are, the numbers that multiply to create it, it's hard to find them just knowing the big number. Computationally, this is hard. We do not have an algorithm that runs on classical computers that can do this efficiently, essentially. And that's all encryption, essentially, is based on certain things being hard to do computationally. This is the problem. This is the hard computational thing that powers RSA. And this is called the integer factorization problem. Is that a question? Cool, good. Please do ask questions as we go. I don't want people to get lost. I know I can go quite fast. So carte blanche to ask questions. So how does RSA work? Well, I would like to take you through a worked example. We have our enormous number that you couldn't possibly factorize, 323. And it's got 2 prime factors, 17 and 19. And this is the number that we're going to use to encrypt some other numbers. In order to perform these calculations, we need to know a certain other number. It's based on our big number. It's called lambda n. It's the Carmichael totient, or the Euler totient of this number. In this case, they happen to be the same thing. And the property of this number is that if you take any number, between 1 and 323, let's say, and you raise it to the power of this secret special number that we need to calculate, then when you divide it by n, there's a remainder of 1. That's the definition of this number. And using group theory, we can find this using some maths that you learn in your first year of undergrad. You can have this relationship where what you need to do is you need to calculate the lowest number that is a multiple of both 16, 1 less than 17, and 18, 1 less than 19. So p minus 1 and q minus 1. That's where those numbers are coming from. And this happens to be 144. This is the smallest number that divides by both 16 and 18. And 144 has the property that any number to the power of 144, when you divide it by 323, you get 1 left over. That will be important later. So what we do with this special number is we say, okay, let's take another number between 1 and 323. It has to share no factors, so we couldn't pick 17 or 19. So I choose 5. Why not? It's a small number. And what we do is we find a number that when you multiply 5 by it, you get 1 more than 144. And this is 29. 29 times 5, 145. 1 more than 144. You could also, if 145 didn't divide by 5, you could keep adding multiples of 144 till you got to a number that did. So yeah, these are some parameters that we are going to use to do our calculation. And these are properties that essentially arise out of, so when we publish our public key, E is part of our public key. So if I want somebody to send me a message encrypted with this system, I say, okay, my big number n is 323, and my little number e is 5. And we keep secret that number, d, 29, that we multiply to get 145. And other people can't know what that number is, because the way we derived it is based on the lambda number, 144, and we got that by knowing the factorization of our big number. So that's why it's hard to derive d from all of these other things without knowing this, right? And that's based on the fact that it's very hard to find the factors of a big number. If someone wants to send us a message, just some numbers, let's say, they can encrypt it. And what they do is they raise it to the power of e. 14 to the power of 5. You'll have to trust me on these. I did them through Wolfram Alpha, well, this one in particular. And that's what they send to us. They send us that modulo n, 323. So they send us these sort of smallish numbers. And what we do at the other end is we say, okay, now we know what number we need to raise it to the power of. We raise it to the power of d, our secret private key, right? And then we take modulus n. And we actually get those numbers back out. You'll have to, this one I really did put into Wolfram Alpha. I did not do these by hand. That would have taken a very long time. Now, the reason this works is because we have this number that we know when you raise anything to the power of it, you end up with a remainder of 1 in mod n, mod 323. So if we multiplied by the same number again, lambda n plus 1, it would be unchanged by this operation. And that's what we're doing when we take the number that was initially raised to the power of 5, we raise it to the power of 29. The way that powers work is that becomes a multiplication. We know that that multiplies to 145, which is 144 plus 1, and now we're in this situation where the number that was sent to us remains unchanged by this sequence of operations. So we can recover the original message, even though all we published was something that would not allow somebody to know what was being sent. How many people have I lost so far? No shame. Right, so the magic here is this number, the definition of it was this number that we can raise anything to the power, and we end up with something that is 1 when you take the remainder of it with our big number. And we're always working modulo that big number. We never need to consider numbers bigger than that. And so by knowing what 1 more than it divides by, we can get to this bit where you decompose that secret number into 2 other numbers, and you only need to publish 1 in order to keep the other one secret and recover the original message. Does that help? Okay, the worked example is not so important as understanding that this crypto system is based on the idea that it's very hard to find the factors of numbers if all you know is the number. Like a big number, and I ask you, what does this divide by? That's hard. And the fact that you can't computationally derive those numbers is what makes this secure. That's the main thing. Cryptography is based on hard maths problems. Sorry? Hello?
So does this mean that the private key and the public can be interswitched?
Yes. If I wanted to publish if I wanted to publish 29 here instead of 5, yes, that would be the same. Those are equivalent. The only thing that matters with those 2 numbers is that they multiply together to make a number. When you raise it to the power, the thing remains unchanged. That help? Excellent. Right, some limitations of the system. You may know that we do not use RSA a lot in production anymore. It requires large prime numbers. This isn't a huge drawback because we can actually compute these fairly efficiently. They are expensive to find, but once we found them, they're pretty useful. If you want to be very efficient with the way that you publish your keys, it makes sense to publish a small number. So again, I chose the smaller number to be my E. If it's very small and you have a really, really big prime number, that means that when you raise something to the small power, it doesn't get big enough that it overlaps and you have to take the modulus of your big number. And that means that somebody can just take the root and get the number back. This is one of the things where, if you're actually implementing RSA, you need to pick a number that you publish as part of your public key that's not tiny, like not 2 or 3 or 5, for example. And the other thing is that this is vulnerable to certain kinds of attack where, due to its mathematical properties, if I take your public key and I encrypt a message that I think somebody is likely to send, now I know what that message looks like and I can keep an eye out for it in your encrypted traffic. But there are certain mathematical properties of the system means that I can actually take elements of messages that I think might be part of encrypted traffic and use certain mathematical techniques to look at the encrypted traffic and sort of decompose the encrypted traffic back down into things that I do know what they are. This is called a plain text attack. Hang on. Yeah, basically that's it. And it's something you can do with RSA, and in order to combat this, we use padding systems, which you can think of kind of analogously as to salt in a hashing function. This is an example of a padding system that was used in 1944. In October 25th, 1944, this message was sent, encrypted, to Admiral Halsey. This was before RSA, by the way, but it's a really good example of padding. In pink, we have things that are just sort of like extra words, padding, to make the message less vulnerable to certain kinds of attacks. We have delimiters in blue, so sort of just a doubled letter there. And then we have the actual message, the actual information in white. And this went wrong because the admiral received this message and he didn't notice that there was a delimiter here, right? When it was decrypted. And the message goes, where is RPT? Where is Task Force 34? The world wonders. And he interpreted this as like a passive aggressive, like, where are your forces? The world is wondering. And he had a tantrum and he went to his room. He locked himself in his room for like a day or something. So, you know, you've also got to use human common sense when it comes to these things as well. But padding systems protect against the sort of plain text attacks that I just described. Right, this is where the abstract maths comes in case you thought that what we were doing before was not abstract enough. The reason RSA works, and the reason elliptic curves, which we're about to cover, work, is because of group theory, which is an area of maths that I love. And you may already, you probably are already familiar with groups, even if you don't know it, because of being able to read the time on a clock. So in a group, this is a group. This is the integers, which is z, modulo 11, right? You count up, and when you get to 11, you consider it to be the same thing as 0 when you start round, just like a clock face. And when we have numbers in this system, we can observe certain properties of the way that they interact with each other. You've got an identity element. When you're adding things, this is 0. This is an element that doesn't change the thing that you're adding it to. It's like a non-op, right? So that's the one there. 0, adding 0 doesn't change an element. You've got things that are the inverses of each other, that when you combine them together, here we're talking about addition, you get back to the identity element. So 10 and 1, 9 and 2, when you add them together, you get back to 11, which is the same as 0. You've got a property called associativity. We're using addition here. This just basically means that if it doesn't matter what order you combine things in, you get to the same result in the end. An example of a mathematical operation that does not have this property is division. So, 1 divided by 2 divided by 3, it matters what order you do those divisions in, you'll get different results. The same is not true for addition, so that means that it's following group law here. And the last property that we care about is closure. If I add any two numbers in this system together, I get back to another number that's in this system, right? And this is done by saying that, well, when you get to 11, you consider it the same as 0. These are the 4 properties of groups. And by recognizing that something follows a set of numbers and a combination operation, something that lets you mush 2 together to get a third, if you know that they satisfy these properties, you can do a lot of very cool maths with it. So far, we have been talking about addition for this group, so saying when you add 1 to 10, you get 11. But we also, in maths, we have, when you add something to itself repeatedly, like 2 plus 2 plus 2 plus 2, we have shorthand for this called multiplication, right? So, for example, 4 times 13 is 52. If we added 4 to itself 13 times, we get 52. But if we added 4 to itself 13 times in this system, we wouldn't get 52 because 52 isn't here. We'd get 8 because that's what happens when you do 52 mod 11, right? But what we've done here is we've said, okay, I've got a number that's in this system and I've multiplied it by something that isn't in this system, but I've still got back to something that is. And this is something you can do when you're looking at groups. Essentially, you can say, okay, I'm going to combine something with itself lots and lots of times, and we're going to call that multiplication. So you can multiply an element of the group by something that's not in this group. So we could actually say, okay, these aren't even numbers anymore. They're just symbols. We're going to combine them. But they still follow this relationship that they have. And this is, this is equally well a group as much as when it was with numbers. We just know that, well, if I add this to itself, I get that. And if I add this to this, then I end up over there. Yeah. But you can still add things to themselves a number of times, right? Everyone with me? Cool. So, now we get to learn about elliptic curves. Elliptic curves are functions of essentially this form. You've got a graph where you've said, okay, it's defined by equations of this form. So A is a number generally it will be a whole number, an integer, and so is B. And they look something like this. They can look a lot of different ways, but this is an example. And what we care about in this graph is the points on this graph where both x and y are whole numbers less than a certain prime. So before, we had z11, right, which is all of the integers but modulo 11. Now we're just looking at some prime. We don't have to decide what it is for the general case. And when you think about the points that are on an elliptic curve that fall in this particular set, you start to see that you've got this nice graph, but actually the things we care about are these sort of disparate blobs, right? And I will show you an example of an actual elliptic curve, not just a sort of abstract representation. And we can define a group with these objects, because what we need to do is we need to define a combination operation, something that takes two of these things and gives you another one. So what we do is we include the point at infinity. We say, okay, infinity and infinity is also part of this group that we're going to care about, this set of things. And we say, okay, if I add this and this and this, they'll sum to infinity if they're on a straight line. We define that to be the way that we combine elements. That's the rule that gives us how we can combine elements. And it turns out that this operation follows all of the group laws, which suddenly means we can start applying group theory to this collection of blobs. Here's a real one. I've stuck with Z11 because we've already used it. You'll notice that none of these points on the curve, well, it's sort of like you could sort of see how a curve could happen here. And none of these points have numbers in them greater than 11, because we only care about the set of numbers between 0 and 10, right? And this curve is given by this equation, and these are the points that satisfy that equation where both the numbers are less than 11. That's it. This is an elliptic curve. We can, there's a worked example of doing the digital signing algorithm with this curve. The way the elliptic curve digital signing algorithm works is, like with RSA, you have to build up a load of parameters in order to do some mathematical operations. These parameters are given by this tuple. And what we do is we go, okay, first we need to care about what number we're doing modulus of. And in that case, it's 11. Now we need to know what we use to define that equation, the equation that gave us the curve in the first place. That's these two numbers. And in the previous case, I think it was 1 and 5. Now we need to care about one of those blobs. We take one of those blobs and we say, this one is our special blob and we're going to use it to do lots of operations with. And we say this is just a tuple and that's its x and y coordinates, both integers less than 11. Next, we care about the order of G within this group. And that means how many times do you have to add our special point to itself to get to infinity? Because remember, we have that combination law that lets us get to infinity. And what is that special number? And we need to care about that. In our case, it will also be 11, which is something that usually happens in this, is that the prime number that you started with is also the same thing as n. That you like that generally for encryption. That makes it more secure, essentially. And the next thing is something you really don't need to care about, other than what I've just said, is that actually this should be 11 and this should be 11, so you like this number to be 1. But that's not, you don't need to know this for now. Yeah, more properly, this is orbit of G. Anyway, so in this elliptic curve, I'm going to show you what each of those parameters are. You've got, here's the thing we need to define. P is 11. Oh, P is 11. I'm going to pick a special point that's my favorite. Oh, no, wait. Yeah. How we define the curve. Now I pick my special favorite point. This is the point that I'm going to say is G. So I put that in there as well. It happens to be that you need to add this to itself 11 times to get to this under that group combination law. Anyway, worked example at the end. But the thing that I want to point out about this is that you've got your special little point, and I add it to itself once, and I end up here. That's by using that group addition law. I did a load of just writing out equations to find this all out. If I add it to itself again, I end up here. If I add it to itself again, I end up here. And as I keep doing that, I cycle around all of the blobs in this elliptic curve. This turns out to be the equations of them. Or this turns out to be the multiplicative chart of that special little point. And you can see we've got inverses like 7 and 4, when you combine those, if you've got 2 points in an elliptic curve and they've got the same x coordinate, but the y coordinates are the negatives of each other, they combine to infinity, and so they're inverses in group law. But what I really want to point out is that we've got back to this situation. I took 1 point, my special little point, and I combined it, and I got to another point, and then again to another. And by doing this multiplication, we found ourselves back in this situation where we're just adding modulo some number, and in this case, it was also 11. So elliptic curves work quite similarly to RSA algorithm. They're based on similar problems in that you've got some prime number and you're going to do some work with it, and it's hard to find out a secret parameter based on the fact that it's hard to do factorization of prime numbers. It's called the discrete logarithm problem here. And the worked example makes it a little bit more clear the ways that they differ. But essentially, elliptic curves work because of some of the same difficult mathematical problems. Hello.
Can you explain how you got this addition? I didn't understand.
Oh, yes. Right, okay. There are some complicated, well, they're not that complicated, but you can, this is what defines the addition law for elliptic curves. And what you can do is you can actually say, okay, these 3 things sum to 0. You can actually say, okay, well, I know that the negative of this is the point down here because it's got the same x but minus y. So I can actually say, actually, these 2 points sum to minus y because I can like move it over to the other side of the equation. Does that make sense? This defines a group law of addition completely. And the way that you actually take 2 coordinate points and sum them is a bit messy, and that's what I spent a lot of time for prep for this talk doing, was like writing out lots of little notes and being like, okay, this is lambda squared, and I do this, and lots of sort of graphs, like drawing gradients and stuff. Yes, when you add a number to itself, what you do is you take the tangent point to the curve at that point. So if I was going to add, let's say, this one to itself, right, I'd take the tangent point, the tangent line, and find out where it intersected the rest of the curve. And then, so it would be that, for example. This is not a well-drawn diagram where it's actually an elliptic curve. Yes, so when you add a number to itself, what you're doing is you're essentially saying, okay, if I add these 2, the result is the negative of the point where it intersects. But if you're adding something to itself, you're taking the tangent rather than drawing the line, because when you draw a line through the same point twice, that's what a tangent is. And you go, okay, where does it intersect? And then the negative of that point will be the addition result. Does that help? This is really, like, this is hard. This is relevant if you want to go through the worked example. The main thing you need to understand here is that we can define a combination rule that gives us a group, and we can start applying a lot of the same theory to elliptic curves that we can to other groups. Does that help? Okay, come and talk to me afterwards, because you want a pen and paper for this stuff, really. I'm sorry. This is one of the reasons that I don't do the worked example in an actual talk, because it just gets, you want pen and paper for it. Right. You can define a cryptographic system of cryptography using these groups, and the good thing about them is that they let you have smaller key sizes compared to RSA. This is great for speed of encryption. This is great for, you've got your YubiKey and it only has a limited amount of memory on it. You can fit more keys on it because they're smaller. You can also have smaller encrypted payloads. So this means that when you're actually sending encrypted messages, the size of those is smaller. This is obviously good for efficiency and faster computation than with RSA, in part due to these 2 factors. So elliptic curves, they're great. I'm aware they're super, super abstract, and I have not managed to sort of go deep enough into them to properly get the ideas into all of your heads, but they're super, super cool. This is all wonderful and great, right? Except we've got quantum computers. So who here has heard of Shor's algorithm? Okay, a handful, right. So in 1994, a mathematician called Shor published some algorithms, some theoretical algorithms for use on, if we ever built a quantum computer, we'd be able to do this with it. And his algorithms essentially defined an efficient way for a theoretical quantum computer to break some of the hard maths problems that power asymmetric encryption. So some of these hard maths problems, we've already seen the integer factorization problem. This is the one that powers RSA. If you have a big number, you know it's result of multiplying two primes, it's hard to find those primes. Some other difficult ones are the discrete logarithm problem. This is essentially, this is what is the thing that powers the elliptic curves, and it's sort of analogous. It's really hard to find the order of an element within a group. It's really hard to find the order of an element such that you can multiply. It's a very simple problem. Sorry, I'm just stumbling over my words. And there's a specific one for the elliptic curve, but this is sort of this is the same problem as this, but specific to elliptic curves, right? These are hard maths problems that power asymmetric encryption. If we could solve these, we could break asymmetric encryption. And what Shor's algorithm does, specifically Shor's order finding algorithm, it says, okay, we've got some big number n. Maybe it's the same n that we use for RSA. And we pick any number a. We can find the smallest number such that when we raise a to that power, we get something that has a remainder of 1, mod n, right? And this lets you factorize integers, and I will show you how. So let n be a number that we use for RSA. We've done 323 before. And we just pick a to be 11. Pick that out of a hat. Doesn't matter. Shor's algorithm tells us, using quantum computing, that if we raise 11 to the power of 48, we'll get remainder 1 mod 323. Don't do this by hand. I spent like 15 minutes with Wolfram Alpha to find this out, because I don't have a quantum computer. This is why you use small examples. Right. And the reason this lets us find the factors of 323 is we can say, okay, we now know that 11 to the 48 minus 1 divides by 323. We can do the difference of two squares. 11 to the 48 is 11 to the 24 squared. So we can do difference of two squares and say, okay, we know that now this, whatever number this is, these things, the product of these two things also divides by 323. So either 323 goes into this entirely, or it goes into this entirely, or there are two or more factors of 323 that are split between these two things, right? We know 323 doesn't divide this thing, or else we would have 11 to the 24 is 1 mod 323, and Shor's algorithm told us we can find the smallest r, 48 was the smallest, so we know that this is not divisible by 323, so either this must be divisible by 323, or it's got some factors and we can find them. So at least some of the factors of 323 must divide this number, right? We can calculate that number, and we can say, okay, what's the greatest thing that divides both of them? Hello.
Was 48 randomly hunting?
48, I went into Wolfram Alpha and I found the smallest r that gives you that result. That I did the thing that a quantum computer would do very efficiently, inefficiently, because I don't have a quantum computer. So this is a real example, and the bit I did by hand that took forever is the bit that a quantum computer would make very efficient for real numbers that are used in real cryptography. Does that help? Cool. We can calculate that the greatest thing that divides both of these two things is not 323, it's actually 17. We can do this efficiently on computers that we have today. We know now, we can look at that number and go, oh my God, that divides our big number. And we can factorize 323. This is essentially, like, the only thing about this process that is difficult right now is the bit that Shor's algorithm gives us, Shor's order finding algorithm gives us, and that's the bit I had to spend 15 minutes on Wolfram Alpha dealing with. This breaks RSA. If you are encrypting things using RSA, quantum computers will break it, and quantum computers break the integer factorization problem. They also break these two by very similar methods. In fact, the elliptic curve digital signing algorithm is even more efficient to break if you've got access to these quantum algorithms. in part because of the smaller key size, ironically. This is bad. We now can't send secure internet traffic, right? Because quantum computers are on their way. People can snoop on traffic, store it forever, in 20 years, break it and read things that still might be sensitive then. This is bad, right? We need post-quantum cryptography. And I've got 4 minutes to go through it, so I will pick up the pace. We need more hard maths problems that are not vulnerable to the kinds of attack that quantum computers make easy. There are more hard maths problems in the world, thankfully, and we can use some of them to power new kinds of cryptography. One is called the isogeny problem. This was first proposed in 1997, so only 3 years after Shor published his algorithms. This describes a non-interactive key exchange protocol where the space of public keys equals the set of FQ isomorphism classes of ordinary elliptic curves over FQ whose endomorphism ring is a given order O of an imaginary quadratic field and whose trace of Frobenius has a prescribed value. I don't know what that means. But I do know that it gives rise to several cryptography systems that have been analysed, and I think all of these ones have eventually been rejected for various reasons. But what they do, so there's Psych and Seed, which are they're considered insecure. I think they were actually broken by a classical computer, but it does show that you can use different hard maths problems to do cryptography in a way that's qualitatively different than RSA and elliptic curves, which are both broken by Shor's algorithms. I love this. This is, an analysis of some of these new schemes based on isogenies and that big long string of maths words that I just said. And it said the conclusion was that the security of some of these systems seems to provide only around half of the expected security. So these systems, based on the isogeny problem, the isogeny finding problem, they're not great, and they probably won't be great. But they show that there is possibility for using different hard maths problems to do cryptography. What is showing promise is something called the learning with errors problem, which is where you introduce essentially noise into your encodings and use probability to then decode at the other end. And I really don't understand this math. I think the isogeny stuff, I have a hope of it. This stuff is outside my area entirely. But what it has done is it's given rise to some algorithms that you can use today. So there's a key encapsulation, so using asymmetric cryptography to exchange keys for symmetric cryptography, which is what TLS does, and also for doing digital signatures. There are algorithms that use this hard maths problem to do these things. And what you do at the moment is, so Google has been working towards making hardware security tokens, like a YubiKey, but I think Google will be producing them, that use these encryption mechanisms. So dilithium is the one that does a signature, like the elliptic curve digital signature algorithm. And essentially, at the moment, the thing that they're proposing you do is you use both at the same time. And this means that even if somebody manages to break ECDSA, there's still dilithium there to protect you, and vice versa. In Chrome, you can enable these algorithms, specifically the key exchange one. And what it does is it does a 64-bit key exchange, and half of it's generated by classical computing algorithms, or these are all classical computer algorithms, ones that are secure against classical computing, and it does half of it that's something that's secure against quantum computing. So even if this turns out to be broken by classical computing, like some other schemes have been, you've still got this, which is still, for now, secure, and vice versa. Signal has also introduced a post-quantum cryptography scheme called PQXDH. Don't know what it stands for, but if you're using Signal, you can be using post-quantum cryptography as well. If you want to know more, this is the organization that's doing a lot of work in this area. I'm tempted to get back into writing C just so I can contribute to their libraries. So things are moving in this direction. Today, you can use post-quantum cryptography algorithms so that your traffic is not vulnerable to being stored and then cracked in whenever we get big quantum computers that can actually use Shor's algorithm to break encryption that we use today. What I hope to see going forward is things like more diverse quantum resilient cryptography. So I showed you a couple of the crystals Kyber and dilithium. It would be nice to see more crypto systems based on more diverse maths problems, so that if, for example, the learning with errors problem, on which the working post-quantum cryptography schemes are based, if that gets broken, if that problem gets solved, those crypto systems go up in smoke too. So I'd like to see more systems based on more diverse maths problems so that we have to solve all of those problems in order to break our encryption. I'd like to see quantum resilient hardware tokens. I'd like my YubiKey to be using Kyber, for example. I think that'd be really, like, apart from anything, it's really cool, but it also means that, you know, your hard security tokens will also be able to use these algorithms. I think that is probably coming in the near future. It's probably a priority for companies like YubiKey. I would like to see these algorithms become more accessible. So at the moment on Chrome, I think it's hidden behind a feature flag. I'm not sure if you can enable it on Firefox. I would like to see these things become more accessible to the wider population and have wider adoption. So wrapping up, I'm aware this has been a really jam-packed, intellectually dense 40 minutes. Thank you for staying with me and for not all of you getting up and walking out. We've been through how we got here, why we need asymmetric cryptography. We've talked about RSA, which is the sort of first asymmetric cryptography scheme, and how ECDSA is analogous to it, both using group theory and the difficulty of finding prime factors and finding the hidden subgroup problem, why they're sort of analogous. And we've talked about how quantum computing is going to change the game, and hopefully, what's next. Thank you so much for your time. I have got a QR code here that leads to a little feedback form. This QR code leads to a little feedback form, completely anonymous, it's just a free text field. These slides I will put up on Twitter. They have sources and they also have the worked example of elliptic curves on them. Please go and enjoy some coffee. Thank you so much for your time.